In Unit 4, we talked about using differentials to get linear approximations. Remember, we said that if dy over dx was the same as f prime of x, we could multiply both sides by dx. Actually, technically, this one is still an equal sign here. And we used then a tiny horizontal change dx to find our tiny, or potentially tiny vertical change dy. Both of those are horizontal and vertical changes on the tangent line as opposed to the actual function, but we can approximate values on the actual function using those differentials, okay? And so this is just a rearrangement of the equation of a line. So this is y2, and it's equal to y1. So y2 minus y1, if you subtract that from the other side, this is the slope, okay? In other words, the derivative at the given point. And this is the horizontal change. So this is the x2 minus x1. So again, this is just the equation for the tangent line and plugging in the original value to find a new value. So Euler's method is just a successive application of using this linear approximation with differentials to find values on a function or even a graph of a function, okay? So we are... and again, using the point on the tangent line to approximate a tangent on, or a point on the curve, just like we did before. We're just doing it multiple times. Okay, so we have a differential equation here. In other words, they're telling us the derivative is equal to just the y-coordinate. Derivative at any point is equal to the y-coordinate. We also have an initial condition of 0, 1, or in other words, the ordered pair 0, 1, if we write the y of 0 equals 1 like that, okay? Now, you don't have to do it as a table. You could write out the equation of a tangent line every time, but my recommendation, this is how I like to do it because it keeps things organized, is I use a table where I plug in my successive values, and that helps me find the new values that we're trying to approximate, okay? So we are trying to approximate the function represented by dy over dx equal to y. Okay, or the group of functions, really. All right, we have an specific particular solution because we have y of 0 equals 1. So let's see, 1, so this is a 2. I don't know where the 1 went. There's a 1 there, and then there's a 2, 6, 8. Okay, so, whoops, sorry, I moved things a little bit here. Okay, I'm starting with a point at 0, 1. I'm going to make this into a little bit better of a table, okay? I'm going to start with my initial condition, the ordered pair 0, 1, so x coordinate, y coordinate, and then dy over dx I get from my equation here. In this case, it's just dependent on the y coordinate. So for the point 0, 1, my dy over dx is 1, okay? Well, according to this right here, to find my new y value, I'm going to take the old y value and I'm going to add the slope times the horizontal change. Well, that horizontal change, dx, is the same as delta x, and so I have it, actually, technically, I guess this should be called the step width. Okay, but I have a width of 1 for my step, so I don't really need to multiply because it's really just times 1. Okay, so I'm going to take the 1 and I'm going to add it to 1 and get a 2. So my second point is at a height of 2, and our horizontal step we've gone over by 1. And really, I'm going to fill in a couple of these. I don't know. We'll see. We'll see how far we need to go. Okay, so now with my slope of 1, I have a point at 1, 2. All right. So now I get that second point. Now, is it a linear piece between these 2 points on the curve? No, but we're just approximating. Okay, and so now repeat on the point 1, 2. Well, the slope for the point 1, 2, or the derivative, is going to be a 2, okay, because it's the y coordinate, and I take that, add it to the original y value, okay, because I'm multiplying by 1, add it to the original y value, and I get a 4. So now I have an ordered pair at 2, 4. Okay, and then repeat again. So at 2, 4, I have a slope of 4 times 1, and then adding to this 4 is 8. So now I have a point at 3, 8. Okay, and hopefully we kind of see what's happening. This is getting bigger pretty quickly. Okay, kind of make it a little bit curved there. And then at 3, 8, we have a slope of 8. So then we would have a point at, one more, 4, 16. And so 4, 16, that's going to be quite a ways up here. I don't know, something like that. Okay, it's going up there. all right? But what we can tell is that we have this exponentially growing function. Now, let's think about what this function is for a second. If this says that the derivative at any point is the y-coordinate, in other words, the derivative of a function is the same as y, the original function, we should be thinking, hey, we know what that function is. That means that y is equal to e of x, because that function is this exponential function that has a derivative of itself. Okay, so it does make sense that this goes up pretty quickly, and that does kind of model e to the x. Now, not quite, because really I should have a point at, if I plug in 1, I should be at 2.7, so really I would be like maybe right about there, and then at 2, e squared is 7 point something, so I'm there. 3, e cubed is, I don't know, e is, well, 3 cubed would be 27, I mean, so it's going to be big. All right, it's going to be something up there. So really, we can see that the further away from our starting point we get, the more inaccurate we are. But the other way that we can address our accuracy is we can change the size of our step, okay? So we're going to repeat this, but now we're going to use a step width of 1/2. Okay, do this in blue. All right, so I'm going to redraw this chart. However, I'm going to add a column. Okay, so I'm still going to start with my x column and then my y column. Oh, those are a little bit thin. My y column, and then dy over dx. And then I'm going to take dy over dx and I'm going to multiply it times delta x. Now really dx and delta x are the same, so this is just like writing dy, but I like to see that extra value, and then that's what gets added to y. Because remember, once again, we take the slope, the derivative here, this is dy over dx, we multiply times dx, or in other words, delta x, and that gets added to the previous y-coordinate to get the new coordinate. Okay, so let's do this again with our initial condition of 0, 1. Okay, let's see if I can make this a little bit straighter. Okay, whatever. All right, so the y-coordinate gives us the derivative, because we're still using dy over dx equals y. Okay, so I have a slope of 1, but now I'm going to take that slope and multiply by my step width, which is 1/2, so I get a 1/2. Okay, now let's go ahead and fill this in. We're counting by halves, so 1/2, 1, 3 halves, 2, 5 halves. Well, let's see how far we need to go. That's probably far enough. So I'm going to take this and add it to, so this, add to this to get the new y value. So my second point is at 1/2 comma 1 plus 1/2, which is 3 halves. So 1/2 and then 1.5. 3 halves is 1.5. So maybe right about, I don't know, there, something like that. Still pretty close. Okay, so there's 2 points. All right, so now dy over dx at this new point, or the slope of the tangent at this new point, is 3 halves, and I'm going to multiply that by 1/2. Again, delta x here is 1/2. Okay, if you want to put a 1/2 right here, that's fine. So then I get 3/4. Okay, so now I take the 3/4, add that to y to get the new y. So now I have 6/4 plus 3/4 is 9/4. So now I have a point at 1 9/4, and 9/4 is 2 1/4. So, all right, a little bit above that. Okay, maybe not right there. Repeat our slope. 9/4 times 2 is 9/8. 9/8 plus 18/8 is 27/8. Okay, 27/8, well, 24/8 would be 3. So we're at almost 3.5. Okay, so 1.5 comma 3.5. So now we're somewhere here, maybe close to the 4 a little bit. All right. Okay, this is looking a little bit closer to the actual approximation, very rough approximation for the curve. Okay, let's do it again. 27/8 is my slope because it's the same as the y-coordinate. Multiply by 2, 27 over 16. 27 over 16 plus 54 over 16. Let me give you a little hint, probably looking for a pattern here. My numerator is just getting multiplied by 3, powers of 3, and my denominator is powers of 2. So move this down. 2. So multiplying by 3, I get 81. Times 3, I get 16. 80 over 16 is 5, so this is just slightly bigger than 5. So now we're at 2 comma 5 point something, maybe right about there. Okay, all right. Again, not quite drawn to scale. We can do one more. So 81 over 16 times 2 is 81 over 32. So again, the next power of 2 is 243 over, okay, we get the hint. 243 over 32. Let's see, 24 divided by 3 is 8. So I don't know, a little bit less than 8. What is that, 5 halves? So 2 1/2, something a little bit less than 8. You right about there? Sure, okay. Either way, we see that we have this approximation for the curve y equals e to the x found by using successive approximations or successive linear approximations using the tangent line. Okay. To generalize this, this is another notation of the same thing that I have right up here, which is the linear approximation. The difference is, like I said before, when we're talking about differential equations, we frequently use this y notation, like y of instead of f of, but it's the same, okay? So given a starting point, x sub 0, okay, and given a derivative of the function, we plug that point into the x coordinate into the derivative, okay, to get this, which is our slope. We multiply it by the width of the step, okay, which the delta x is going to be the same every time. You're going to use widths, steps that are the same width. We add that to the original, ooh, don't know what happened there. We add that to the original value to get, there we go, to get the new height, and then we repeat from there. So then y of x2 would be y of x1 plus y prime of x1 times delta x2, which is just delta x. Okay. Don't try and memorize the formula. Just understand that you are finding the slope, meaning derivative, multiplying it by the horizontal change, and adding that to the original y value to get the new y value, and then you repeat, okay? All right, so as we do this, this is generalized even further, where we start with the nth term and get the n plus 1th term, and then, repeat. Okay. Move this over a little bit. So when we do this, I guess I can make it a little bit smaller. When we do this, we are going to need to find a few things. We need to know our derivative, okay? Implicitly or explicitly defined, doesn't matter, but we need to know what the derivative is. We need to know our initial condition. So this is usually going to be written as an ordered pair. If not, then you have well, actually, no, you are going to always be given the whole point. Okay, so this is the initial condition. And then the step width or step size. Okay. All right. So also a problem will tell you how many steps to use. Okay. Or it'll say get from here to here, or, approximate this using this many steps, and then you can figure out the width of the step. Okay. So we have a derivative of negative x over y, and we have an initial condition of 3, 4. We're looking for the approximation for y of 4. We want to use Euler's method and 2 steps. Okay, so we're taking 2 steps. All right, so I'm going to draw my chart because I like to organize it like this. So x, y, and then dy over dx, and then dy over dx times delta x. Delta x, let's figure out what delta x is going to be. Well, I need to go from 3 to 4 using 2 steps, so delta x is going to be 1/2. All right, so this is 1/2. Okay, initial condition is the ordered pair 3, 4, and I'm going to go 3, and then so 7 halves, and then 4, and then so I will be done when I get to this spot right here because I will have 4 comma something. That's my approximation for y of 4. All right, so my slope is negative x over y. Let's plug that, 3, 4 into that, so we get a slope of negative 3/4. Make this a little bit bigger because I'm already writing small. And then I'm going to take that, multiply by 1/2, we get negative 3/8. I take that value, and remember we add it to the previous y value, so I add 4 plus 3/8, so I'm doing 32/8, minus, it's negative 3/8, so we get 29 over 8, okay? 29, oh goodness, look at this fraction math we're doing already. Okay, that's all right, I believe in us. All right, so into negative x over y, that's going to be negative 7/2 divided by 29 over 8. So in other words, negative 7/2 times 8 over 29 is going to be negative 28 over 29 when I reduce that, okay? And then I take that and I multiply by 1/2 and I get negative, oh, sorry, no, not negative because it's the opposite of, oh no, we did that. Yeah, we did the opposite. Okay, so negative 14 over 29. Okay, so lastly, I need to take negative 14 over 29, add it to 29 over 8 to get the new value. You will not have to do, you will not have to do this kind of arithmetic by hand on any kind of assessment or anything. This is one that I may have just made up without checking to see if it works well or not. Okay, so we need to get a common denominator. 29 times 29 is going to be 30 times 28 plus 1, so 6, so 841. Okay, so we've got 841 minus 14 times 8. I'm just getting a common denominator here. 14 times 8 is 80 and 32, so 112 over whatever 8 times 29 is. Figure it out in a second. 841 minus 112 is 742 minus 12 would be 30, so 729 over 8 times 20, nope, no common factors. 729 is a power of 3, so 8 times 29 is 160 plus 72, so 232. Goodness. 729 over 232. All right, so y of 4 is approximately that nonsense. Okay, again, you won't have to do that kind of arithmetic by hand, but I didn't really check when I made it up.